In this lecture, we are going to review complex numbers, complex number theory. So what do I mean by a complex number? A complex number is a number that has both a real and imaginary part. So for example, here we have this number z, which has a real part a and imaginary part b, or jb, or b is what we call the imaginary part. J in electrical engineering is what we refer to as square root of minus 1. Mathematicians will call it I. We call it J. It's just the way it is. We can't explain ourselves away, but we just call it J. So A plus JB is a complex number with the real part A and imaginary part B. We will be running into complex numbers because we will have complex impedances for our circuits. We've ran into complex numbers already with solving second-order differential equations, and because when we solve the roots of a characteristic polynomial. So for example, if I want to find the roots of an x squared plus x plus 1, I use a quadratic formula. So it gives me a minus 1 because that's my b value. A and c are also 1, so I get minus 1 plus or minus square root of 1 squared, minus 4 times 1 times 1 over 2 times 1. Since 1 squared minus 1 is a minus 3, that gives me a square root of minus 3, which is j times the square root of 3. So therefore my roots are minus a half plus or minus j times square root of 3 over 2. So I have a conjugate pair of root. Conjugate means that they're the same real part, same magnitude of the imaginary part, but difference in sign. Okay, so the roots of this real equation has a conjugate pair of roots. Okay, these are, can't say this is undefined, these are actual roots, which are conjugate, which are complex roots and coming in a conjugate pair. So the conjugate pair has real parts, the minus a half, and the imaginary parts are plus or minus square root of 3 over 2. So we're looking at when I say z equals a plus jb, we say that is the rectangular form of a complex number. We can also express this in a polar form. Well, we can think of this as, since a and the real part, the imaginary parts are actually independent. It's a quadrature type relationship. That is, I can never have a real part contributing to the imaginary part, or imaginary part can never contribute to the real part, so they're completely independent. So we can put this, treat this as two independent variables on an xy plot. So we call this a complex plane, in which on the x, or the horizontal axis, we will plot the real part of the complex number, and on the vertical, we will plot the imaginary part. Okay, so these axes span from minus infinity to plus infinity, and they cross at the origin. So for example, here I have it, let's say a is a negative real number, so I would just find my a on the horizontal. B, I'll assume it's a positive number, and I put that b on my positive imaginary axis, and the intersection of the horizontal vertical lines are my complex point z on the complex plane. So this circle here is my z point coordinate. Now, we can also say, okay, well, I can treat this as a vector from the origin to my complex point. That vector has a length, which I refer to as being the magnitude of the complex number. And this vector makes an angle phi off the positive real axis. I call it the angle of the complex number. So this is like a polar form in a cylindrical coordinate frame, where I can have an xy coordinate and write it as a rho phi. But here I'm going to write it as a magnitude and phase, we refer to these. Okay, so magnitude of z is by the straight line, z straight line, that refers to the magnitude of the complex number, and phi is the angle off the positive real axis. Well, if I look here, I actually have this forms a triangle along the vertical and the horizontal, with the hypotenuse being the vector. And the height of the triangle is b, the imaginary piece. The base of the triangle is a, the real piece. The hypotenuse is the magnitude of the complex number, which is this length, which we know from Pythagorean's theorem is simply square root of a squared plus b squared. Is the length of the hypotenuse. We also know that the angle off the positive real axis can be found by the inverse tangent of b over a. And that gives me the angle of my complex number. Here, a is negative, b is positive. I'm in the second quadrant. Therefore, my angle is going to be between pi over 2 and pi, as I would expect. In polar form, I can say my complex number that has a magnitude z times e to the j phi. Remember, phi is the angle in radians. Or in angular form, I can write the z angle bracket, phi, and this we generally use this notation when angles expressed in degrees. Okay, of course, I can always cast degrees into radians by multiplying by pi over 180, or vice versa. So this is the polar form of a complex number. Now to convert from polar back to rectangular, we can apply what's called Euler's law, where Euler's law says that my E, or Z, magnitude Z, e to the j phi, or angle phi, is equal to the magnitude of Z times the cosine of the angle phi, plus J times the magnitude of Z times the sine of the angle phi. Okay? And so magnitude of Z times the cosine of the angle is my real part A. Magnitude of Z times sine of the angle gives my imaginary part B. Well, if I think of that, all that is cosine is the projection of phi onto the horizontal axis, right? So even though, or since cosine, this phi angle here shown is greater than pi over 2, that cosine is going to give me a negative number. So magnitude of Z, cosine of phi gives a projection A, which is a negative number in this case, on the real axis. Magnitude of Z sine phi gives a projection on the vertical axis. Okay, so hence, this is how I would convert my polar form back to the rectangular form. So for example, 4 angle 30 would be 4 cosine 30 degrees plus J4 times sine of 30 degrees. Since the cosine of 30 is root 3 over 2, that would give me 4 root 3 over 2, or 2 root 3. For a real part, and since sine of 30 is a half, then 4 sine 30 just gives me 4 over 2, or 2. And that's how I would convert that to rectangular form. Okay, and just to review again, to go from rectangular back to polar form, we use Pythagorean's theorem. The magnitude is a squared plus b squared, square root of that sum. The angle is the inverse tan of b over a. But what I want to point out is you have to, if you just plug this into a calculator, you have to be cognizant of the quadrant, because the sine of b over a is not sufficient to determine phi. You actually have to know the sine of b and the sine of a in order to determine phi. For example, let's say both a and b are positive. Then we're going to be in the first quadrant. And therefore, phi has to be between 0 and pi over 2, right? And the ratio of b over a, of course, since both are positive, the ratio is also positive. So knowing they're both positive, then I know I'm going to be in the first quadrant. If I'm in quadrant 2, a will be negative, b will be positive. I know that my phi angle is going to be between pi and pi over 2. The ratio of b over a is negative, yes, but because b is positive, a is negative, I'm in the second quadrant. Okay, if I'm in the third quadrant, both a and b are negative. And therefore, if I'm at a plus pi to minus, or minus pi to plus pi angle, then in the third quadrant, phi is minus pi to minus pi over 2. Or I could say it's between pi and 3 pi over 2, same thing. The ratio of b over a is greater than 0. Well, wait a minute, in quadrant 1, the ratio of b over a is greater than 0. But since I know that both b and a are both negative, I have to be in the third quadrant. So if I just put this in my calculator, it would actually give me an angle, phi, and I'd have to add or subtract pi to that angle, or 180 degrees from working degrees, to get the angle in the third quadrant. In the fourth quadrant, a is positive, b is negative. Again, the ratio of b over a is less than 0, which is the same as in quadrant 2, where b was positive, a was negative. But knowing that I'm in quadrant 4, because a is positive, b is negative, then my angle must be between minus pi over 2 and 0. Most calculators just do the ratio of b over a will give you an angle between minus 90 and plus 90, or minus pi over 2 and plus pi over 2. And you, as the calculator, that is the person using the calculator, will have to add or subtract 180 degrees if you know you're in the opposite quadrant. Okay, so just be aware of that. Okay, we mentioned this property of a complex number called its conjugate. All right, so what do we mean by that? If I have a complex number with a magnitude z, mag z, and angle phi, I can find its conjugate, which here I'm using notation z superscript star. That is what I'm calling conjugate. Some references will put it over bar, z over bar. But z conjugate is then has the same magnitude, but the negative of the angle. Okay, so it's the same magnitude, we just negate the angle. That's how we get a complex conjugate of a complex number. Well, in rectangular form, let's look at the impact of that. So let's look at convert this polar value to rectangular form. We'll have a cosine of minus phi, because cosine is an even function. That's just is equal to plus cosine of phi. Sine of minus phi is a minus sine of phi, because it's an odd function. So therefore, I see that z conjugate has the negative imaginary, or it negates the imaginary part of z. So we have two properties then of complex conjugates of numbers. One, we negate the angle in polar form, or we negate the imaginary term. Okay, so that's the definition of a complex conjugate. Graphically, if I have my z angle phi, as we did before, with a actually positive, I flipped these, it should be positive b, negative a. I take the conjugate of that, I just negate the angle. Okay, so what I do is simply negate the imaginary part. It's not 180 degrees rotation. Nope, it is negating the angle. Okay, so or negating the imaginary part. So the red dot here is the conjugate of the blue dot. Well, one interesting thing about a complex conjugate is that if I multiply any number by its complex conjugate, so I take a z as a plus jb, and I multiply it by its conjugate, that should have been a b here, sorry. And if I multiply it by its conjugate, then this theorem says I'm going to get the magnitude squared. Well, let's prove that. Let's take the product of z with its conjugate. And so I can do this in long form by taking a plus jb times a minus jb, which is the conjugate of z. Multiply a times a, that's a squared, plus jb times a, that's jba. I take a times a minus jb, gives me minus ajb, plus jb times a minus jb gives me a minus jb squared. Okay. Well, I notice that these jba and minus jba's cancel. J squared gives me a minus 1, so I get a minus minus, and that just gives me a squared plus b squared, which is equal to the magnitude of z squared. So indeed, z times its conjugate equals the magnitude of z squared. Okay, it's a nice property to have, because if I want to find the magnitude of a complex number, I just need to take it times its conjugate and take the square root, and that gives me magnitude of the complex number. Okay. So two things. Complex number times its conjugate is its magnitude squared. We also see it gives me a positive real number, always. That's an important property to understand. Okay, so we need to be able to do operations with complex numbers. So for example, if I'm given two complex numbers, I have a 4 angle 30 and a 6 angle minus 45. This vector here is my 4 angle 30. This vector here is my 6 angle minus 45. And I want to add these two complex numbers. Okay, so that is, I want to add the complex numbers. But it's difficult to add complex numbers in polar form. So what we need to do is first convert these to rectangular form. So apply Euler's law. 4 angle 30 gives me 2 root 3 plus 2j, plus 6 angle minus 45 gives me 3 root 2 minus 3 root 2j. And now I can add a rectangular form. Why? Because the real pieces add and the imaginary pieces add. So I can add my 2 root 3 plus my 3 root 2 is my total real part. 2j minus 3 root 2j is my total imaginary part. So therefore, this gives me the real part is 7.707, which is the sum of 2 root 3 plus 3 root 2, plus an imaginary part, which is minus 2.243, which is the sum of 2 minus 3 root 2. Okay. And of course, I can convert that back to polar form if I want, which I will in a minute. But what I want to show you is we can also do this graphically. That is, I'm going to add z1 plus z2. I can take z1, I'll take at the end or the tip of z1, I'm going to trace z2. And so when I'm adding these two vectors, I by default will be adding the two real parts and the two imaginary parts. And that gives me my purple curve here, which is the sum of these two vectors done now graphically. And then in polar form, this purple curve vector will have a length or magnitude of 8.026, which is the magnitude of this complex number, and an angle of minus 16.225 degrees, off the positive real angle. Or I can express that in radians as 8.026 e to the minus j 0.283 radians, or 0.283 is pi over 180 times 16.225. We can similarly subtract two complex numbers. Let's subtract z2 from z1. Again, I don't want to do that in polar form. I'm going to convert these to rectangular form and just simply subtract. That means my real pieces subtract and my imaginary pieces subtract. Graphically, this is the same as saying z1 and adding to it the vector minus z2. So this is actually minus z2, which is just z, the same angle off the real axis, but flip direction. Okay, so I begin my vector at z1, trace minus z2 from that point, and that gives me the subtraction z1 minus z2 by adding z1 plus minus z2. Okay. Or I can write this in polar form as 6.29 and an angle of 97.11 degrees. It's a plus 97.11 degrees. Okay. Or I can put that in polar, in terms of radians, 6.29 plus j, 1.695 radians. Okay. Well, how do I multiply complex numbers? Let's say I want to multiply z1 and z2. So I take z1 times z2. Well, I can do this in rectangular form, right? I can write these two in the rectangular form and then do all the cross products. So I get 2 root 3 times 3 root 2 plus 2j times 3 root 2 plus 2 root 3 times the minus 3 root 2j plus 2j times the minus 3 root 2j. So what I see is that the product of the two real terms gives me a real number. But it turns out the product of the two imaginary terms also gives me a real number because it gives me a j squared, which is a minus 1. The product of the two cross terms gives me imaginary numbers. Okay, because it's a real times imaginary will always give me an imaginary number. So these two contribute to my imaginary terms, and the real part times the real part and the imaginary part times the imaginary part gives me contribution to my imaginary terms. Okay. So my two real terms gives me the real value of this product, and the cross terms, real times imaginaries, gives me the imaginary terms of this product. Right? So I sum up my two real terms and my two imaginary terms, and I have a result of 23.182 minus j 6.212. Convert that to polar form. A squared plus b squared square root gives me 24. Arctan of that gives me minus 15 degrees. Because it has a negative real part, negative imaginary part, positive real, I'm in the fourth quadrant. Okay, well, there's an easier way to do this. That is, I can just go ahead and multiply in polar form. Because in polar form, I can just simply multiply the magnitudes. 4 times 6 gives me 24. And this is the same as saying e to the j phi 1 times e to the j phi 2, which I know is equal to e to the j phi 1 plus phi 2. Same thing in angular form is I can simply add the angle. So I can add 30 plus a minus 45, okay, which gives me minus 15 degrees. So I simply multiplying the magnitudes and adding the two angles. I can do multiplication in polar form quite trivially. All right. Well, I can also divide two complex numbers. Let's do that. So I can divide z1 with z2. So here I define, this is a plus 45, so I just kind of flipped the sign here arbitrarily. So I just choose, I'm going to divide 4 angle 30 with 6 angle 45. Okay. So I can do this by putting this rectangular form, but it's going to be a pain to divide this complex number to this using long division. It's a simpler way to do this. That is, what I could do is realize, okay, I want to get rid of this complex number, the denominator, so why not multiply by its conjugate? So I know if I multiply top and bottom of the conjugates, multiply by 1, I'm guaranteed to have a real number in the denominator. Well, that's a whole lot easier to divide. Okay. So if I do that, then I can multiply z1 times z2 conjugate over z2 times its conjugate, which is magnitude z2 squared. Okay. Or if I see this in terms of products, because I'm adding the angles, well, I'm adding 45 with its conjugate, which is minus 45, these will give me 0. So it just gives me magnitude squared. And I get the product of Z1 with Z2 conjugate. Okay, well now I can just multiply the magnitudes and add the angles. So I get 4 times 6, angle 30 minus 45, over 6 squared, but these two 6's cancel. What I see is this is the same as dividing the magnitudes and subtracting the angles. All right, so if I'm dividing two complex numbers, it's easiest to do this in polar form. I can do that by dividing the magnitudes and subtracting the angles. Okay, so this gives me a 2/3 angle minus 15 degrees, which turns out to be in rectangular form 1.644 minus j 0.173. Okay. All right, so in summary, we have not exhausted complex number theory, but we've given a sufficient introduction, hopefully practical use of it. Complex number expressed in rectangular form as being a real and imaginary part, a plus jb. We can convert this to polar form with magnitude and phase, z e to the j phi in radians, or z e to the z angle phi in degrees, where magnitude of z I can get by square root of z times its conjugate, or it's equal to square root of a squared plus b squared. Phi is equal to the inverse tan of b over a, but I need to know the sine of b and the sine of a to know which quadrant I am in, all right, in order to get the right angle for phi. Next, when we add two numbers, we just simply do this in rectangular form. We add the real parts and the imaginary parts, okay? Subtract, and I just simply subtract the two real parts, subtract the imaginary parts. We're going to multiply two complex numbers. I multiply the magnitudes, I add their phases. I'm going to divide two complex numbers, I divide the magnitudes, and I subtract their phases, where the negative phase, of course, is the the complex number in the denominator. The reason why it's negative, as we saw before, is because we're multiplying effectively by the conjugate, top and bottom. All right, that completes our review of complex numbers.